First, I would like to thank Jürgen, Robin, and Christina for inviting me. It's my pleasure to be here and to be talking to you about power transmission with universal pulses. So we had all these mind-sharing sessions yesterday. I think a lot of us expressed the fact that RF inhomogeneity was really one of the most important obstacles on our way to exploit ultra-high field scanners. So I think I will spare the introduction of what the problem is. But before I dive into the subject, I thought I would list what I consider perhaps arguably the different important milestones in the community. So the first one was the birth of power transmission with 2003 catcher, but it was for accelerated multidimensional pulses, and it was Gregor, I think was here, who actually presented this technology as a potential way to mitigate the RF field inhomogeneity problem. Then there was a spatial domain method, I think, that made our life easier because it was a convenient and elegant way of describing the problem. We also have to acknowledge the B1 mapping efforts here. I think 15 years ago, it would take us 45 minutes to acquire 8 three-dimensional B1 maps over a brain, and now I think it is just boils down to a few minutes, and I think it helped us to just test our developments to do that. Then also the VOPs were the game changer. You heard it before, is that, before we had to deal with hundreds of thousands of constraints, perhaps even a million, and now we end up with a few hundreds, or maybe 1,000, and it's much more tractable from a numerical point of view. Algorithms also with smarter metrics, smarter approaches to deal with the known convexity of the optimization problems. Also smart parameterizations like spokes or QT points for 2D and 3D, because you don't want too many degrees of freedom because you want a fast computation. On the other hand, you want something to be efficient to be able to reach good performance. And finally, I think we have to acknowledge the efforts done by the whole community to push and validate our RF coils and become more confident in their use and exploit them more. And also we have to thank Siemens for their efforts when it comes to exam supervision. They really made a big effort when it comes to that. So needless to say, this is a technology that works. In my opinion, you've seen many illustrations. This is a non-exhaustive list, but you have many different contrasts, many different sequences using 3D, 2D pulses, refocusing, non-linear, large flip angle pulses. It works. There's no doubt about it. And you can, if you have the expertise and you have the financial means and you have the equipment, obviously, you can really solve this problem and restore a good homogeneous excitation profile. But the problem has been for a long time the workflow. Because when you accumulate the time it takes to measure B1 maps, we can argue about the numbers, but I'll come back to that later. Measure the B0. You want also a certain resolution if you want to define a brain mask with automatic methods. If you have a 2-course resolution, then the brain masking procedure may not give you good results. There's also data transfer and analysis, and I would be a little bit more or less optimistic than the previous speaker when it comes to calculation time, when you take into account a whole exam with the non-linear flip angles you have to deal with, the multi-band approaches, and all of this. That's a lot of pulse and a lot of non-convexity to address in one exam. So I think it would be more in the ballpark of 5 minutes for an overall exam and for thorough optimization. So total, it's 12 minutes. You can live with that, but I think in routine, it's a no-go. And experience has shown that not only you need expertise to run this, but you can always expect some delays and some problems. Sometimes they were just human errors. We would just click on the wrong button. Sometimes they were technical problems. So we really wanted to solve this problem. And so we came up a few years ago with this solution called plug-and-play universal pulses. So here, I'm just showing you the history, how it started. We had a homemade coil with 8 transceive elements. We had a certain number of subjects scanned, and we simply looked at the maps. And well, among here, these 12 subjects, of course, we can see differences, but we can see also a lot of similarities. So we thought about trying this numerical experiment. We didn't know if it was going to work. And we took the first half of these subjects and we called them the database subjects. And we simply took all the time we needed to do a thorough optimization on all of them simultaneously. In other words, we wanted to mitigate the RF imaging problem simultaneously on all these subjects while being robust respect to these inter-subject variations. And the way to do that is simple. You calculate the performance on subject 1, subject 2, up to subject 6 or more, and you take the average. It gives you a solution that we baptize actually universal pulses for obvious reasons, and we simply then apply them on another set of volunteers who were not in this initial database. And we skip entirely the calibration procedure and no pulse design whatsoever. It really feels like a single channel kind of exam. So we tried that in vivo with the MP Rage. It led to our first paper. We were happy, but for a broader scale solution, obviously we needed to redevelop the tool for coil that is available at other sites, right? So far it was done with the homemade coil. So we started the same adventure, this time with the Nova parallel transmission coil. We didn't have that coil by then, so we collaborated with the Tony Stoker's group, and it's been great to work with those guys. And now, from now on, we work with a database of 20 subjects. The age ranges from 20 to 60 years old, half females, half males. And we use the B1 maps in amplitude, phase, and B0 map as well. So each sequence has specificities, different targets, different metrics, refocusing, inversion, you name it. I'm not going to go into the details, but instead I'm going to just list the different results we have obtained so far and the different achievements. So first, with a 3D acquisition, with the KT point parameterization, the most straightforward one was the MP Rage. So what you typically get with the quadrature mode of excitation is this bright centering effect and also some losses of signal or contrast in the occipital temporal lobes, but also in the cerebellum. And with the universal pulses, then you nicely get rid of this bright centering effect, and you also recover the signal and the contrast that you expect. And we have replicated that on tens of volunteers. For the turbo spin echo or the space, that was an interesting problem. That was a new challenge, and I have to say that the theory was really fun because it was a different challenge because now you don't know the state of the magnetization prior to your RF pulse. It can be anywhere on the Bloch sphere. So you don't want to synthesize uniform flip angle throughout the brain. You want to synthesize uniform rotation matrices with the transverse axis of rotation. And we were happy actually to working out the theory that you could still use this KT point parameterization, and actually the solution that you get is scalable. So you can use the same single pulse to use in variable flip angle train. So this is the result of the quadrature excitation mode, which reminds us that for T2-weighted sequences, actually RF homogeneity is a killer, and this is what we got with the universal pulse. And on 4 additional volunteers, you see that we could observe more or less the same thing. These are the sagittal views, and then it appears straightforward to just extend this to the flare with single inversion. So we have this TSC module, and prior to that we have an inversion time and inversion pulse to suppress the signal from the CSF. So you can see it works. You can suppress that signal. You can mitigate the RF imaging problem. However, you can see that the signal for white matter and gray matter is quite weak. This is a limitation of the sequence and not of the RF pulses. So what you do is that you replace this by a T2 preparation, still using universal non-selective pulses. And now what this does is that it inverse the CSF magnetization while saturating the gray and white matter magnetization. Therefore, you boost the signal of the later tissue, as shown right here. And again, without any calibration or any pulse design whatsoever. Finally, for anatomy, double inversion recovery with your 2 inversion pulses and 2 inversion times. If you tune them correctly, then you can suppress not only the CSF signal, but also the white matter to be more sensitive to potential lesions. And again, it works. Let me switch to 2D acquisition now. So with the CPU mode of excitation, typically what you get is that this dropout of B1 as you go lower in the brain, and you can see it pretty clearly here. And again, now with selective universal pulses based on the spokes approach, what you do is that you have a pulse which is designed for each location with respect to the isocenter. And you can nicely mitigate that. So we pushed that further, this time with the multiband approach. So we replicated the resting stain fMRI HCP protocol, multiband 5, and I think Ben will talk a bit more about this. And we just scanned 5 different subjects, comparing the performance of the PTX approach compared to the single channel and single channel with pads. And the results in TSNR were shining. Now, if we want to disseminate this for the people who have, or the sites who have the same coil as us, well, we need to test whether it would still work. So we got inspired by these traveling heads efforts done by the Goofy here in Germany. And the question was, even if you have the same coil, can there be a tiny manufacturing detail that would possibly spoil the performance? We didn't know, so the only way to know was to try. So we worked a lot with Bonn, DZNE, of course, from the beginning. We also went to Maastricht to work with Ben and Chris, and we also sent the pulses to the University of Minnesota, and each time we said, please take the pulses and press the button. Just don't ask any question, and let's look at the results together. So we have accumulated over 60 volunteers across those 4 sites, and so far we've not encountered any failure in terms of performance. So we have this package of sequences, anatomical sequences, where the pulses are directly embedded in the sequences. There are no external files. The SAR and the power limits are handled by the sequence, and it's called PASTER, and it includes the MP range, the MP2 range, the turbo spin echo, the flare, double inversion recovery, and the GRE, and we look forward to doing the same actually for the Terra. Something relatively new is that we have started also clinical study with this package on MS patients, so that the scan incorporates these different sequences. So this is here the standard exam you run at 3 Tesla with 1.3 millimeter isotropic resolution, and now with 70 and this PTX technology, we get higher resolution, no B1 artifacts, and we see the lesion quite well, but somebody could argue, well, I already see it pretty well at 3T, but however, you can find other spots here that are barely visible at 3 Tesla. Finally, also another result is that one penalty we had to pay so far is that, for instance, for the space sequence, the refocusing pulses were a bit longer than what you would have for the CP mode of excitation. So they were 1 millisecond long, and the CP mode hard pulses typically are 700 microseconds. But we have made some efforts, and now we optimize those duration. It takes longer actually to calculate this, but for universal pulses, that's not a problem because nobody's in the scanner waiting for you to return the solution. You can take as much time as you want, and therefore it gets more performance, but also actually when you repeat this experiment and you shift your transmitter frequency by 200 hertz, you calculate the difference and you normalize, then you find that indeed you're more robust with respect to B0 inhomogeneity, and for higher field than 7 Tesla, I'm sure this is going to help. Okay, so let me conclude by doing a comparison between universal pulses versus the subject-based approaches. Well, first of all, what we have observed is that indeed, when you use the subject-based design, it takes less energy. To be robust with respect to inter-subject variations, you need more energy simply because you need to be more broadband. That said, it's never been really a limitation in all these experiments I've shown you before. Also, because you dedicate your optimization to a particular subject, yes, it's going to be a little bit more homogeneous, a little bit more performance. But I would argue that this is in the ideal condition, meaning you must have accurate B1 maps. If you go too fast, then you're going to pay a price in accuracy. If there is motion, because you acquire your B1 maps at the beginning of the exam, then the motion is going to affect the B1 map and your performance is going to be affected. Also, thorough optimization. If you spend 1 second doing a nonlinear flip angle optimization, you're going to not get great results. So with all that, I would say that in the non-ideal scenario, it's not really clear actually which one would yield the best performance in that case. Safety assessment also, because you have pre-computed solutions. If you're not so sure about the safety, just take a phantom and measure the temperature rise as much as you want. In the other case, the solutions don't exist until you actually run the scan. So you have to rely 100% on numerical simulation. You can also modify the exam at will, because there are no calculations, no region of interest to draw. You can change however you want the exam and do whatever you want. Then no expertise either. This is also a complex field, a lot of jargon, a lot of questions. It's simply complex. And here, you just don't ask any question and you let the experts do their jobs. And then finally, perhaps most importantly, no time penalty. So if you take the instance, the UK Biobank of 100,000 subjects, you multiply that by 10 minutes, that's 2 years of saving time. And that concludes my talk, and thank you very much for your attention. I would like to thank also my collaborator across the ocean, but also in Europe, for participating in this nice adventure. Thank you.
Thank you, Nicolas. We're open for questions.
Testing. Fantastic. This is definitely a path forward, right, for making the PTX usable. I was wondering, for the VOP that was used for this, is it the standard VOP that came with the 8-channel array for the Nova Medical Coil, or?
So there are no standard VOPs coming with the Nova Coil. EM simulations are provided. These are just the raw field maps, and it's your responsibility to process them and validate them and make the VOPs yourself. So this is what we've done.
Maybe that was a question for Renee, but but I'm wondering, on the new system, on the Terra, we'll have the 8-channel coil, and it will come with the VOPs apparently. So
that's my understanding. Yes.
So that model, I imagine, would be appropriate also for the whatever universal pulse is provided or you design. Is that connection correct, or is there?
I would assume so, but you never know. I don't know the details behind their procedure, at least not yet. So I cannot really say it for sure. I mean, we typically take safety factors behind all of this, and if I don't know what they are, it's almost impossible to predict right now. But for sure, there's going to be some efforts to port all these developments to the Terra. And we'd be happy to work with Siemens on that.
Great, thanks.
Other questions? Peter over here. And
Thank you. So there are a number of us who have still got the Magneton version of the 7T, and I'm sure we would benefit from all of the great work that you've done. Can you let us know where you've got to with being able to share the universal pulses amongst the Magneton community?
Well, I hope soon, but this is a question you should ask Siemens. Yeah.
Okay. Anybody from Siemens would like to answer?
Very nice work. The power of PTX for sure can homogenize the entire brain, but I believe another thing is you can also focus in a specific brain region. So I'm thinking maybe in future you can also develop some universal pulses for, let's say, I just want to study the occipital lobe or the frontal lobe for different purposes. So you can have this package for the whole brain, have the atlas, and do the matching, and then I just focus on one brain.
So you're talking about IVI, like inner volume imaging?
Yeah, well, just excite the.
Yeah, so we've not really done so much on IVI, but I know in Tübingen they're trying something on that subject. Yeah.
I was looking at your list of universal pulse. I didn't see any for EPI, 2D or 3D echoplanar imaging. Do they exist for those type of sequences?
Yeah, so the multiband we did was with 2D API multi-slice multiband, and for the 3D API we have done it. I don't know if Ben is going to talk about it, but it's included in the 3D API as well. Yeah.
Maybe I was surprised you mentioned when you were talking about your balance of the different things. You said you hadn't really run into issues with SAR, and so the power penalty for universal pulses wasn't a big deal. But I mean, even with fast TR multiband API, we run into SAR all the time. So I'm curious. Why you said that, or is it only under certain conditions? Or?
So I would think about two explanations. First, from my experience so far, the Nova PTX is really a good coil, and it's very efficient from the transmit point of view, and it's been a relief to work with that coil. So it certainly helps a lot. And then the second explanation is, I would say, it's the power of the algorithms. You have so many degrees of freedom to play with the SAR and the SAR hotspots that it finds a way. Now for the multiband, I would say that this is the only sequence where we reached that limit. We reached the threshold of the 10 gram SAR, but for all the other ones, we were a factor of 2 below at least. And including safety factors.
Okay. All right. Well, thank you very much. Terrific talk.